There's a ton of people all sitting in Slack actively waiting for this.
Okay, we're live.
Hello, everyone.
Uh,
Can I have a chat link?
yeah,
Actually, I don't need a chat link. I have Slack.
but there's two
Somewhere.
chats.
Yeah, I know. Actively waiting for.
Yeah.
I don't have four screens like you do. Nancy says, "We see you."
Yes.
So I see that Peter over on Slack mentioned they invented time at Greenwich. And one thing that has always amused me is I now live on the 90th meridian. So I am literally a quarter turn of the planet away from Greenwich. So that's 6 hours. This is how I always remember where I am in time
Yeah.
relative to Greenwich. Oh, it says Fraser has no sound.
I have no sound?
That makes no sense.
No, I totally have sound.
Peter? Was it because I was doing all the talking? That's entirely possible.
Definitely says that I'm using the right device.
Oh, it says Dr. Gay is loud, Fraser not so much.
Yeah. Classic Pamela, super loud.
Sorry.
No.
I'm super caffeinated. That doesn't help.
Yeah. Oh, me too. Me too. This is going to be a party. Yeah. All right.
Recording is when I discover where all of my messes are.
Yeah. All right. Let's do it. Okay. Oh, wait, I should say hi to some people. The people who, followed along to this strange time. Hey to Arnold Post and Bill Druin and Brian Stabb and Guido Bieber and Helge Bierkog and Holly Meyer and James Haney, John Seffield, Quad Libet, Nancy Graziano, Nicola Williams, Nora Kisher-Brown, Peter Quinn, Peter Woof, Ricky Buxton, Thomas Traniker, Tiago Avalar, Umu, and Yamagashi-san. Hello, everybody. Man, it's raining so hard here, and it has been raining here for days. It's actually at this point, so we get a lake in our backyard every winter as the sort of the water.
Can you ice skate on it? Can you ice skate on it? Can you ice skate on it?
No, I live
that
in
sucks.
a rainforest.
I know, but you sometimes get massive amounts of snow.
You could boat around in it. You could row around in my backyard when it gets bad enough. But no, you can't ice skate in it. It's gone. It's gone. If it's snowing, then it drains away within a day. So no. Okay. We tried to build an ice rink once in our backyard, but it just didn't get cold enough. Just doesn't get cold enough here.
That is sad. That is very, very sad.
No, I guess. I don't know. Do you want it to be wet or do you want it to be cold? Choose.
I like having 4 seasons. Thank you very much.
Yeah. So there you go. We get cold and wet, but not cold. All right, let's do this episode of Astronomy Cast. Tell me when you're ready to click on.
Oh, Fraser, Nancy says it looks like you have a wrong chat on air.
I have the AC live chat.
Okay. I'm going to move on then.
Is that the wrong one?
I think that's the right one.
Yeah.
AC live chat.
Mm-hmm.
Okay.
Yeah.
All of Europe is already drinking.
That's awesome.
Okay.
Man, those poor people from that space beer company. So there's this company that's made beer, Ninkasa or something like that, and then they reach out to us and they're like, hey, do you guys drink beer? Would you like some beer?
Yes.
Yes, please.
The answer is yes.
Would. Yes, absolutely. And then they're like, I'm like, but can you send it to Canada? And they're like, wait a second, I don't know. And they're like, nope, turns out no. So I've just been taunting them now. So when your influencer outreach goes horribly awry, and so I went and had some beer yesterday or 2 days ago, but it hadn't been to space, So non-space beer. So anyway, it was pretty funny.
I am so grateful for beer, first of all.
Oh, I'm sure it's
And
going to be. I'm sure it's going to be delicious. I'm sure it'll be lovely.
I've heard several people say amazing things about this and taunt me that they're drinking beer with yeast that went into space.
Yep.
I have not had this experience yet. And now I get to be one of the cool kids. And usually Fraser gets to be the cool kid because he lives on the West Coast and I live in the flyover zone.
Yeah.
So yes.
Yeah, we have a lot of really cool microbreweries and stuff here. So, and it's an imperial stout. Yeah. Why? Quadley would ask, why can't they do it? Is it Canada like Narnia or something? I just think alcohol is not permitted across the border without all kinds of rules.
Yeah, you have to have special exporting, importing rules, and you can do it friend to friend, but this clearly would not count as friend to friend.
Yep. So anyway, now their social media outreach is backfired, and all they do is just get me taunting them every time I have beer that's never been to space.
But you are giving their beer lots of free.
I guess so. I guess I am. All right. Let's begin this episode. I'm going to press record.
Okay.
All right.
Yes, I should press record too. I have pressed record. Wow. I'm very jet lagged, very caffeinated. This is going to be a great episode, Chad. Sorry for what we're going to do to you.
All right, let's do it.
Okay.
Astronomy Cast, episode 467, Resonance. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today. With me is Dr. Pamela Gay, the Director of Technology and Citizen Science at the Astronomical Society of the Pacific, and the Director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. We are recording this episode at a funny time. Where are you off to now?
I'm actually going to go on vacation before the marathon of astronomy that is what our reality is every winter begins. So I'm actually going to go hang out with some of the people that we've met through our various Astronomy Cast trips over the years.
Yep.
So I'm going to go to Disneyland and Universal Studios.
On the West Coast.
And on the West Coast. And so I get back and jump straight into the marathon that is helping my colleagues who are going to the American Geophysical Union prep for that conference, prepping myself to go to the American Astronomical Society meeting.
Right. When's the next AAS meeting?
It is second week of January in Washington, D.C. I will be there this year. I'm going to probably have a small fleet of students with me. We're still getting permission from their professors, though.
Yep.
And so it's going to be all science all the time. And I just wanted to get a little vacation in before I do that.
That sounds great. You've earned it. I permit it.
Yes, I needed me some Disney.
I've been to that place 3 times, I think, in Universal Studios 3 times.
I've never been to Universal. This is going to be my first time there. And I have to admit, I'm the kind of nerd that I tried really hard to find Ravenclaw leggings before I go, and they only make them for like 12-year-olds, and I'm not 12.
We'll have a great time. I just want to remind everybody who is listening to this podcast as an audio podcast, the regular stream, you are actually only getting half the show. So we actually do a full hour of the show. Half of the show is what you're listening to, but the other half is we just stick around and answer people's questions. We talk about news, we talk about philosophy, things that are happening in our world. And so if you want to hear more of the banter, that's in the full feed. And somewhere there are instructions on how to access the full feed, but you can do a search for it, Astronomy Cast, the full feed, and you get the raw recording experience. If you want more of the content and more of the up-to-date news stuff, things like that. So check that out if that's what you want. And also, give us some kind of ratings and likes on iTunes and all the various social medias. That helps a ton. All right,
that's all we want for the holidays. All we want is good reviews.
All we want is good reviews. Or bad reviews with constructive feedback.
That's true.
All right. So
but if you can email those.
Many of the moons and planets across the universe are in resonance with each other and their star. What causes this resonance, and how can it help us understand the history of planetary formation and migration? Resonance. And this topic was recommended last week during our live show, and it was like this gap in our armor that we had not. We talked about planetary migration, we've talked about formation and stuff, and we've talked about the moons of Jupiter and things like that, but we haven't actually gone into this idea of resonance, and a lot of it is fairly fresh in my brain. I'm doing an episode of The Guide to Space about planetary migration and talking about resonance. It's a really fascinating topic and comes up time and time again in astronomy. So I'm amazed that we hadn't did a whole episode of this, which is great. I love it. So let's do it. Resonance.
So the best place to start, I think, is just what is this concept of resonance? And essentially, it's that if you add energy to things at a particular frequency, you can drive their behavior. My favorite example of this, because it is so counterintuitive, is swings in a swing set. If you have two side-by-side swing sets, one of the like cheap short ones that you get and put in your backyard as a little kid, and then one of the really tall ones that they have in schoolyards, those two different sets of swings will swing the kids at very different rates. And it doesn't matter how far back you pull the child, the rate at which the swing swings is determined strictly by how long the chain on the swing is. And if any of you know of some place that has baby swing set next to giant swing set, and you can recreate this experiment, I want that video desperately. So please send us your videos of swing sets side by side, or edit together side by side swing set swinging swings.
Right.
We want this for the sake of science.
Of science. We've actually got a swing set on the local mountain nearby here on our ski hill, but it's like an adult sized, like it's a super swing. And so it's probably maybe 6 meters tall. So it's like just a huge swing. And so when you're swinging, it gets kind of terrifying as you're going back and forth. So another rabbit hole. Okay, so that's so how does resonance play into this idea of swinging? What is going on? What is the resonance part of this?
So with a swing set, you have this set natural frequency of the swing. And if you want to get a kid going at a higher and higher swing, a higher swing of their swing, I'm not quite sure how to verb that. If you want to do this, you have to provide energy to them at the same frequency at which they're swinging. If you try and add that energy in anywhere else, you're just going to screw up the system. So imagine you were chaotically running underneath the swinging child and randomly adding energy to their swing at all sorts of different intervals. You're probably not going to do anything to successfully get them swinging higher and higher.
Right. And I think we've all experienced that when you get the timing wrong and you get the wind knocked out of you, as opposed to gently adding a little bit of speed to the person's swinging.
And this idea that if you regularly add energy at the correct frequency, you can end up greatly changing the behavior of the system. This is where resonance comes in.
Okay.
So we've seen many different examples of this in the physical world. The Tacoma Bridge is one of the great examples they make all of us watch in school.
Yeah, we watched that in engineering.
Exactly. And so the period of oscillation is related to the length of something and the power of gravity. And bridges are basically a long string, and you can pluck them just like you can pluck a guitar string. And if you add energy to them at just the right frequency, they will oscillate. And in the case of the Tacoma Bridge, it oscillated itself into oblivion.
Right.
It collapsed and died. And there was actually the London Footbridge over the river. It also had the flaw that human beings tend to naturally walk with a set frequency. And its resonant frequency happened to match that of human beings walking. And so people were actually feeling ill, and the bridge was vibrating from all of these footsteps driving oscillations in the bridge. So we have to be careful to not add energy into things, or to purposefully add energy into things at the correct frequency. With human beings, last week he brought up the concept of this brown note, where human beings have a natural frequency ourselves. We are, after all, nothing more than a string filled with water. Well, scientist after scientist has tried to find a frequency that if you blast human beings with sound waves, dire things will occur. I will leave the user to figure out on their own what brown note might mean. Now, no one has ever succeeded in making anyone have horrible automatic gastrointestinal reactions in the downward direction.
So you're debunking that.
Yes.
Yes.
However, what has been found is that you can cause nausea, you can cause shortness of breath because of the way the air is getting resonated inside the human. And NASA, being NASA, they knew that it wasn't air that would be conducting the resonance to their astronauts. It would be the seat of their pants.
Right.
And so they took the early astronauts and stuck them in a chair and resonated the astronauts physically and found that you can make them feel quite nauseous, right, and you can make it hard for them to think, hard for them to move, because you've hit the natural frequency of the human being.
Right.
So don't do that.
Don't do that. No.
Just don't.
Yeah. So let's talk about some other situations. And the one that I sort of introed was this idea of orbital resonance. So how does the resonance of planets and moons match swinging on a swing set?
So it comes down to this idea of adding energy to something in a systematic way. If you're going along happily in your orbit and you ever so randomly hit the gravitational pull of other objects at various places in your orbit, it's probably not going to have a sum of all of these things affecting your orbit in a meaningful way. Now, if every single time you hit the exact same place in your orbit, you have energy added due to an extra bit of gravitational pull from another object, over time, this is going to increase or decrease your orbit depending on how it's happening. Now, what's kind of amazing is because of all of the conservation factors that go on. It's a matter, if you look at how does the gravitational force acting over a distance change, exchange energy, do work, and you also have conservation of momentum coming in. So all the cool physics, you can give really evil homework problems with this. And the bulk result is you take a planet, call it Saturn, you put it into resonance with Jupiter so that the two of them keep lining up around the sun at the exact same place.
Right. So your Jupiter will go around twice for every time that Saturn goes around once.
And then you litter the solar system with small things. Asteroids, comets, rocky things, icy things, things that are between rocks and ice that we don't know what to call because we lack imagination. You litter the solar system with all of these things. As they have their orbits changed systematically, they give up their angular momentum to these planets. So if something keeps getting shuttled around by Jupiter and Saturn, let's say Saturn is the primary instigator here, it's going to get flung into the inner part of the solar system And due to conservation of angular momentum, Saturn is slowly going to migrate backwards, getting further and further out. And it's believed through the Nice model, which is named after Nice, France, which is why it looks like the word nice and is not pronounced that way, that there is this point in our solar system's history where we had the giant worlds in all of these different resonances and a solar system that was still filled with stuff. And due to a combination of all of the stuff they had to fling and these orbital resonances, the worlds got moved outwards, the stuff got moved inwards, and the inner worlds got thwomped violently during what we now refer to as the late heavy bombardment.
Right. And so there's a neat... we talked about this at the end of the show last week, and it wasn't in the regular feed, but this idea that for many of the planetary systems, what the sort of the perfect simulated version of this is that you've got this big disk of material. These heavy planets are born and scoop up material inside this region, and then they start to kick out objects that they encounter that have gotten a little bit bigger. And as they kick them out, this causes them to lose orbital momentum, and they spiral inward until they reach sort of a clear spot in the solar system. And then they stop.
Or hit something.
Or hit something, sure, right? In the simplified version. And then you get sort of the next planet out moves in, and what puts the brakes on those planets from moving any further in is this orbital resonance. Once they hit this orbital resonance, that's when they settle down. And so for a lot of the planetary systems that people are finding out there, especially for the ones that are close into their red dwarf stars, you're seeing these orbital resonance. When the forces of gravity are so strong, things line up and get into this balance, this music.
And we see this with the Galilean moons of Jupiter quite clearly. And this is actually the kind of observational experiment that anyone with even a moderately sized telescope can do for themselves, where when you look to see how all of the happy little moons line up, there's this Io going around zip, 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 zip. Then you have Europa going around and it's 2-1. You have Ganymede and 4-1, and Callista's in there as well, but I don't remember what Callista's resonance is. And so with this fabulous set of resonances, you have beautifully circularized orbits. You have tidal heating, which is what allows Europa to have these vast oceans and Io to have these amazing volcanoes. And it's just awesome. Now, unfortunately for the planets, while it was awesome, it was also highly destructive. You might be thinking that just how much momentum can one little icy body give up? So when you look at our asteroid belt has the total amount of mass of about, I think it's 0.4 of the moon. Now, all of the stuff that is theorized to have got flung around in the Nice model was actually 35 Earth masses. So we're looking at tens upon tens upon tens of times the amount of mass that is in the asteroid belt was flung into the inner solar system.
Yes, helping to cause the bombardment. And this is the point, right? Is that these worlds, you know, the process of getting into that level of resonance, you know, you either get on board or you get out. You get in line or you get out. And that's but in the end, I mean, the amazing thing about the planetary formation and migration in our solar system was that because there was so much material and there was so much chaos and moment and sort of mayhem that happened, they couldn't settle down into that perfect orbital resonance. They got as far as they could go, and then they just ended up in the place where they are with everything cleared out and not having the resonance. And so things are strange. Like Neptune is bigger than Uranus, but it's farther out. the worlds are more spread out than they should be. They're not as far packed into the sun as they would be if things were clear and things were more stable and happened better. They couldn't reach that resonance that they wanted to because of all this debris.
And according to this one particular model, the outermost world started out at 17 AU, and that outermost world was probably Uranus. Neptune and Uranus somehow got flopped in which one is further out, and we ended up with Neptune out at 35 AU. So it essentially doubled the distance of where the outermost of the known worlds is. Now, what's going to be interesting is to see how things change and how this model has to be upgraded as it is required to take into account the new world that we're desperately trying to find that is causing Sedna and everything else to have such wonky orbits. And so this is Michael Brown's team that's doing these observations. And then there's also computer simulations going on, because when the NICE model was done in 2005, first of all, it was one of our first episodes of Slacker Astronomy, so you can hear us squeaking about it happily in Slacker Astronomy if you go dig out the episode. But second of all, computers were not as good in 2005 as they are today. And folks like our friend Kevin Grazier have been working on doing more modern models that are better able to take into account all the different pieces, all the different probabilities, and essentially do a much more fine-grained simulation. And first of all, there may have been a whole lot more stuff that got expelled because it doesn't really make sense that the stuff was only flung inwards. We know that today Jupiter is an equal opportunity destroyer and send things outwards as well as inwards. And when you take this into account, how does this change planetary migration? When you add in this new world, how does that change the models? So we have a lot of new stuff, and I for one am eagerly awaiting to see what new simulations come up with in the future. But we know that resonance is a thing because we do see it all over the place.
Yeah, and a good example of that is the TRAPPIST-1 system, where it's got all of these worlds and they're orbiting quite tightly and close to their star, orbiting around and around, and they're in a resonance. And there's a really interesting piece of music that someone created where they put all of the planets and made them be musical instruments, and then you could hear the resonance as they go over time, and it absolutely sounds like music because it's just got these matched up beats, which music does. Now you talked about, I mean, this is one example, but I remember like even last week as we were setting this up, you're like, oh, and there's masers, and there's some other topics in astronomy where resonance comes into play.
And so we have the positive resonances of things that are like the Galilean moons, like the TRAPPIST worlds lining up. We also have negative resonances. So this is the Kirkwood gaps in the asteroids, where if you try and find an asteroid that's at 2.06 AU, you're probably going to have a really hard time doing it because that would put it into a 4-to-1 resonance with Jupiter. And most of these Jupiter resonances, 3-to-1, 5-to-2, all of these different resonances, for the most part, are kind of mostly devoid of asteroids. So we have asteroids that are taking away, as well as we have asteroids that are adding things in. Now, we also do find throughout the rest of physics really cool effects of being able to use resonance to play with particles, to play with light, which is neither a particle nor a wave and is both a particle and a wave. Figure out however you want to phrase that.
Yeah.
And
has a certain duality to it.
It does. It is of mixed nature. And so when you're building lasers, you have what are called optical cavities that are designed to get all the light going back and forth um, in a way that it resonates together. This is a super simplistic way of saying it, but the idea is basically you have an optical cavity or a resonating cavity, and this creates waves of light the same way when you pluck a string, you have waves on the string. Now, with a string on a guitar, you don't have to worry about saying this string will not resonate if it's the wrong length, because the string adapts. Light does not. Light is like, I am green. You cannot ungreen me. I shall not resonate. This string, this cavity is the wrong size. So you have to very carefully tune the size of your cavity to the color of the light you are dealing with to get the laser you wish to have. And it's just kind of cool that space, it turns out, has different ways of, in the microwave, creating basically artificial cavities that allow space to generate the microwave version of lasers, which is called a maser.
Right.
And
which is like the best
those are
name.
just awesome.
Yeah. And so there are these natural lasers, and it's essentially the same thing. I mean, laser light and microwave light are just two versions of light, just further on the electromagnetic spectrum. So that's amazing to think about that. And that the universe, I mean, we see it with the orbital resonance around with planets and moons, so it's not surprising that this resonance appears in other times and generates these things. But it's still a pretty fascinating concept. Did we do an episode on masers? I think we did.
I think we did.
Yeah.
Or at least we brought them up within the context of lasers.
What is the underlying mechanism of a maser?
I'm pretty sure that it's water. Sorry, Chad, you're going to have to edit this while I look this up. Maser, they have them around Jupiter. Maser in space. You are now learning that I don't remember everything all the time. Underlying mechanism. It's pumping a population inversion. Sorry, Chad.
Water molecules in star-forming regions undergo a population inversion and emit radiation at 22 gigahertz, creating the brightest spectral line of the radio universe. And they are associated with active galactic nuclei, which are megamasers, which is an even better name. We can skip that if it's
let's just skip this, Chad. Sorry. Yeah, I was like ready to jump to Fabry-Perot interferometers, and you went somewhere completely different, and my brain did not go with you.
You want to talk about interferometers?
I do. So let's jump from lasers to instead how you can actually subtract light instead of adding it.
What?
Okay, I will artificially add a transition in, Chad.
Yeah.
Chad, we're sorry, Chad. We like you, Chad. We really, really like you, Chad. Okay. So
it's perfectly fine to have my confusion baked right into the episodes of Astronomy. Don't remove that, Chad. Feel free to have me go, what? And be confused and a little surprised at the possibilities of the universe throws at us. So what on earth were you talking about?
So lasers, so just like the resonances that we have with orbits can either taketh or giveth, where you either have things like the Galilean moons happily resonating and generating awesome, or the asteroid Kirkwood gaps that are happily taking away. With light, we have lasers, which happily have this cavity that leads to population inversions, awesomeness, and bright lights that we can use to torture cats who don't understand they can't catch light. We can also use this kind of resonance in what's called a Fabry-Perot system, an interferometer, an etalon, to remove light of unwanted colors. So you shine starlight into a system that has carefully spaced surfaces that both transmit and reflect light in different ways. And what will end up happening is the only light that's able to get transmitted through the system is stuff that has the correct wavelength for the given cavity size. So you can tune this sucker to see different colors of light thanks to cavity sizes and resonance and all of this awesomeness. And it's just kind of cool. And this gets back at this dichotomy of interference, like we talked about last week, resonance, which we're talking about this week, and how all these different physical factors work together.
One sort of from spaceflight reporting that we dealt with back in 2009, I don't know if you remember this, but the International Space Station has a resonance to it. Like any physical object, you said bridges, right? And so there were these rockets attached on one of the modules, and they would boost the space station from time to time. And so the rocket was firing at the resonance frequency of the International Space Station, and so the rockets kind of gimbal, and so you can watch this video and you can see the whole space station jiggling and the rockets kind of gimbaling around as it's doing this.
And they don't do that anymore.
No, I'm reading this. I'm reading Endurance, the book by Scott Kelly about his year in space, and talking about how they, after that event, they've changed the way they boost the space station to try and avoid that resonance. Because if they just kept going, would things have shaken loose? So it's it's a problem out in space and with rockets. You can imagine, when the space shuttles launch, they shake badly, right?
Mm-hmm.
When these rockets launch, and a lot of the times the pools underneath the space shuttle and stuff, a lot of that is their acoustic damping, and their job is to stop the sound waves from coming back up and hitting the rocket again and tearing it apart. And I don't even know if you're getting even into resonance. You're just getting into the destructive damage of these acoustic waves that are being done to these rockets. But the resonance would take it to the next level. You get that rocket shaking from its own sound, thing will tear itself apart. So,
and what is so cool is they actually have at, I believe it's Goddard rather, a vibration chamber that they stick things in that they're planning to launch to vibrate the bejesus out of them in a safe environment where they can turn off the vibrations if they discover they're hitting a resonance. And they will change how spacecraft are packed, how they are folded up, what ballast they have around them, to make sure that the common frequencies encountered during launch are not the frequencies that are going to shake apart spacecraft.
And one last note, Guido is saying this in the chat, and normally I don't bring this stuff into the episode, but he's exactly right, which is the treadmill. So the treadmill on the space station, when someone's using and running on the treadmill, it causes a resonance in the space station that has been of concern in the past, and so they have to dampen the treadmill so that it doesn't shake the space station, which is just an amazing idea. All right, well, we're at the end of our time. Pamela, thank you so much for talking about resonance this week. Have a safe trip, and we'll see you. Hi, Eddie. And we'll see you. The podcasters have no idea what just happened. The dog just busted into the room behind her. You can just tell the time. We'll see you next week.
See you. Bye-bye, everyone.
All right. Save, and then...
You want to come up? Come on up. You're now going under the desk. That is the opposite of coming up. Come on up, baby. Come on up. I know. Come here. Come on up.
Aww. Man, that dog is a handful. Having finally experienced that dog He is an intense handful. He is on the move. He is always the center of everything, and is high maintenance.
He's a herding dog.
Yeah.
He's not so much high maintenance as he's high energy, and you have to use the energy. And normal day to day, I can like take him out on my bike and run him ragged, but that hasn't happened yet today.
Yeah. No, ours are not that. Ours are pretty intense though, but one of them anyway. Is even though she's 10, she's pretty intense. All right, so you know what to do. Go ahead, put some questions into the chat if you want, and we will answer your questions about space and astronomy.
What episode number is this?
This is 467.
Thank you.
Let's see if there's anything there. Someone had a question that came up. So this comes from Astro B. There must be a resonance in gravitational waves as well. So the gravitational waves cause waves, but it's objects that have resonance. So it's not the gravity waves that are going to have the resonance. The gravity waves are going to have a frequency. And one of the things I talked to a physicist, asked them about gravitational waves kind of passing through your body, and that if you were close enough, they would tear your body apart if you were close enough to the objects that were gravitationally waving. So you can imagine if there's some kind of permanent gravitational wave that's, some object is generating constant gravitational waves, and those gravitational waves are hitting the resonance of some physical object, then you would get resonance going on. Badness, yeah. If things weren't already bad enough. Oh, there you go. I hear a dog wanting to come in. Hold on, I'm going to grab my dog. Love dueling dogs.
Almost at episode 500. So at only one episode a week, we are a long ways from 500.
Yeah.
we will get there, but yeah.
Jordan Couch is asking, did you know that the resonant frequency was used in the 1930s to destroy pathogens in the human body without any harm to human cells?
That works.
That works. I know they use resonance or they use sound waves. I don't know if it's resonance. That doesn't sound true to me. Do you have some some article about it? Because you think if they could destroy pathogens in the 1930s, they would be doing it now, but at an industrial scale. You'd be sitting in your home resonance machine.
Sonic showers would be a thing.
Yeah, that'd be great.
I want a sonic shower.
Quadlibit wants to know if Planet 9 is out there. Did it get there because it was kicked out?
Don't know.
Yeah. Yeah, maybe it got captured. Maybe it was flung out. Maybe it formed in place and it stayed outside of the mayhem of everything else. We just don't know.
And this is why we science. It's because we don't know everything and we want to.
Yeah. Step one is find it.
Yes.
So, anything else? Any questions? If not, I gotta run a kid to a class, so I might shut things down a little early. Let's do that.
So we do have Patreon office hours starting in 10 minutes.
Perfect.
Patrons, you know the link. I'm going to figure out what Eddie just stole from my recycling bin and is now destroying under my desk.
Nice. That sounds good. Let's wrap it up.
And I'll see y'all in 10.
All right. Sounds good. Okay.
Bye-bye.
Bye.